that was what happened last time. No, sorry, that's not what happened last time. Oh, fantastic. Yes, thank you. But this is the one with the empty batteries. So it's flashing, so it's battery empty. Then this is we have solved the energy problem.
That's a timer.
Oh, I see.
It's not zero because...
Oh, then I've thrown away many laser pointers for no good reason. So, I'll be talking about unphysical simulation. I'll try to explain what I mean, but the main message, and it's basically elaborating on what I said before I started, is that I've been not been working on liquid crystals for 10 years, and so whatever I'm going to tell you is very old stuff. Now, the advantage is that millions of papers are being published every year, so almost certainly most of you have not read what I've done long ago, and so that's probably what's going to save me. For the others, it's going to be a bit of comic relief. Good. A very brief introduction about liquid crystals, in particular lyotropic liquid crystals, and the role of computer simulations. As many of you will be aware, if you have particles with purely excluded volume interactions, you can have a very wide variety of liquid crystalline phases. So if you start from an isotropic liquid of rod-like particles, as you increase the density, you can get a nematic phase, and actually that is the thing that Onsager already worked out in the 1940s. What computer simulations shown since is that if you then compress it, you can get a smectic phase, purely entropically driven, and in a sense independently, because it was first shown for hard spheres, but then also for hard rods, you can get a crystalline phase. And there are many more phases that you can get. I just show as one additional example, if you have disk-like particles, you can get this phase, the columnar phase. I mean, you can also get the nematic phase, but you can get at sufficiently high density a columnar phase. And this is one of those nice examples where the simulations were first and the experiments were later. So the only thing I want to say about this is that there are many different phases that you can get that purely form because the entropy of the ordered phase at some point becomes higher than the entropy of the disordered phase at the same density. Now, what I want to do today is to discuss specifically what we can learn about from looking at limiting situations. And so I will look at limiting cases, but actually looking at limiting cases is pretty much the very first thing that happened in this field. Because if you look at Onsager's work, he of course considered the formation. Well, I mean, he was interested in the observation that in suspension of tobacco mosaic virus in the 1930s, people observed liquid crystalline order, and he tried to work out an explanation that argued that this was due to entropy alone, excluded volume alone. And then the paper is a masterpiece because he had to first make it plausible that it was excluded volume interactions, and all then show that once he'd shown that the interactions behaved like effectively hardcore repulsion, then he went on to show that that was enough to get an isotropic nematic transition. The important thing in Onsager's model, he is smiling at you, is that he considered rod-like particles with a length L and a diameter D, and then focused on the limit L over D going to infinity. So infinitely, it's almost like this rod, but slightly extended to infinity. And so the reason is, why did Onsager consider this limit? Now, in science, you never are supposed to ask the question why, because that's left to God. As Onsager is very close to God, you should also, when you question Onsager, you should also not ask why. But anyway, there are reasons why even we can understand why it's useful to consider this limit. So, very briefly, the physics underlying the Onsager isotropic nematic transition. If you have a disordered fluid like this, particles point in all directions, the most likely relative orientation is perpendicular, and under those conditions, a pair of particles have an excluded volume that is twice the diameter times the length squared. So it's basically you have a flat square box with a thickness 2d and a side L that is excluded. So that's a fairly large excluded volume, certainly if L goes to infinity. In contrast, the excluded volume, if the two rods are parallel, is much smaller because this is d squared L and this is L squared d. So this is of order d over L smaller than that one. So if you go to the limit of infinite aspect ratio, the excluded volume here is eventually infinitely smaller than the excluded volume there. Now, of course, in a nematic phase, rods are not perfectly aligned, so you never really get to this situation. But you can see how, if you have particles that are aligned, they exclude less volume to each other, so that as a consequence, they have more, they have a larger volume accessible, and therefore they have a higher entropy. And so the higher translational entropy, they pay for it by lowering their orientational entropy, but at some point that trade-off becomes favorable, and you go from the low density isotropic phase to the high density nematic phase. That is in words what happens. But now, in a bit more detail, how do you make that into a theory? And so then you say, well, I will have to look at the conditions for coexistence between the two phases. And then if you consider a system at the same temperature, we talk about hardcore particles, so temperature really doesn't play a role. The other things that matter are that the pressures are equal and the chemical potentials are equal. Now, okay, so if you start from the low density approach, and say, sorry, in the case of the pressure, what I would have to do is I just write down a virial series, and of course that series may or may not converge. I mean, I should say for a more mathematical audience that for systems with sufficiently short range interactions, these series converge in an almost negligibly small range of density, but it's not totally zero. So there is some evidence that sometimes these series actually work. In general, actually, we don't know, but we hope that there's a relevant range where these series do converge. You can write the pressure, and I write it here as the dimensionless, the compressibility factor PV over NKT, which for an ideal gas is 1. It's a virial series. And similarly, you can write down the chemical potential. And the chemical potential has a leading term KT log rho, which is just the ideal gas, and the term, and then everything else is due to interaction. And actually, exactly the same virial coefficients in a slightly different form come back into the excess chemical potential. Now, why is it very convenient to start looking at a model of extremely long rods? The reason is that the series stops. And this is something that Onsager conjectured. He never really said that he proved it. And I think basically, I'm still unaware of a proof, but then I said, I've been out in the field for a while. But numerically, the evidence is very strong. So if you look at the higher order virial coefficients for hard spheral cylinders, so here you have the aspect ratio. This is a sphere. This is 10, 100, 1,000, 10, etc., up to 1,000,000. And you look at the ratio of the third, the fourth, and the fifth virial coefficient compared to the second virial coefficient squared cubed of the fourth power. You see that this ratio becomes very, very small. So here, typically it goes down by almost a decade per factor 10 in the aspect ratio. And so these numbers, by the way, you see that they can also be positive or negative. So actually, for the rods, as far as I know, it is positive, negative, etc. As you would continue, although I think that few people would have the energy to continue once beyond that, in particular because these things are so small. The important thing is these things really become negligible, and as a consequence, Onsager could truncate his whole theoretical description at the second virial level. Now, I'm not going to try to really explain why the higher virial coefficients vanish, but I'll try to use a hand-waving argument, which is pretty much the best I can do anyway. So if you have B2, the B2, the second virial coefficient, is 1/2 the excluded volume between two rods. So basically means you fix one rod and you integrate over all positions of the second rod that intersect the first rod. And if the rod has a length L and a diameter D, that integral of the position of the second rod is of order L squared D. Now we go to the third real coefficient, and in the third real coefficient, it's convenient. There's only one diagram that counts, and it's actually all three rods intersecting. So we fix the first rod, we move the second one, and for instance, it will give a contribution L squared D. And then the third one, we move over all positions. The second one gives me another contribution L squared D, but actually it has to intersect the first one. And if you have to intersect the first one, now let me do something very mathematical right on Blackboard. If you have to intersect the first one, then basically what happens is, here's the first rod. It's coming out of the blackboard. Here's my third rod, and it has to intersect. So I'll just draw a line. It has to intersect, something like this. And so you have this angle theta that actually tells you the range over which these two things can intersect. And theta will be of order d over, well, in general over L, but this distance need not be L. It can be anywhere between L and 0. So let's call it its order d over x, and then I have to integrate. Sorry, I shouldn't mix it up. Then if I integrate, I do something like d over x dx between d and L. And then you see you get something that looks like log L over d. And then I average over all positions, so then I do 1 over L here, 1 over L there. And that's what you see on the right hand side. So if you look at all the possible orientations, you get the correction to this vector L squared d that is of order log L over L. And for sufficiently large L, that goes to 0. So the reason, and again, this is not a proof, but this makes, and that same argument holds for all higher real coefficients too, even though I guess nobody has really looked at all possible diagrams to check whether that really is correct. But in principle, I'm pretty confident that's right. So that is why it is convenient to use this limit, because then you can work out the theory by going in the isotropic phase only to the second real coefficient. Now, what it means is that if you go to the low density phase, you can work out the excluded volume between two rods. It is actually, the excluded volume is 2L squared times the sine of the angle. You average over all angles. This is three-dimensional, so average over cosine theta. And the net result is that you get an excluded volume that is of order, well, I said, of order L squared d. And if you now use that to get the second real coefficient, the second real coefficient is 1/2 the excluded volume. If you do that, then you can do the rest. You can write out the pressure. Actually, I write the density. This is the number, that's the rho, the number of particles per unit volume. I multiply it by the second real coefficient to make it dimensionless, and I call that thing C. So this is a dimensionless density, just to make things easier. Then the pressure in those units is C times 1 plus C, so that's basically saying that in those units by construction the second real coefficient is 1. And you can write down the chemical potential, and it's log C, which is the KT log rho term, and divided by 4 pi, that's the orientational average. And this is the excess part due to the interactions, this is the second real part. Okay, so this thing is, no matter what theory you use, as long as you have long enough rods, this bit is always true. The hard part comes if you go to the pneumatic phase, because there you have to either use approximations, and on site I used a particularly good approximation, although not perfect. Theo Odijk used a much simpler approximation, a Gaussian one. I'll sketch it in a few lines in a minute. Or you actually have to write down the density functional and then just solve the density functional, to minimize the density functional explicitly numerically, and then you get the quote-unquote exact answer. But of course that's not exact in the mathematical sense, it's exact in the sense that you can get it as accurate as you like. So let me just give one example of how you do such a thing, and I'll take the Odijk approach, where basically say in the pneumatic phase we assume that the orientational distribution is strongly peaked, so up and down of course are symmetric, but otherwise it's strongly peaked, and the assumption that is made is that you can write the orientational distribution. Oh, there should be definitely a minus sign here, otherwise it's a very unpleasant orientational distribution function. But this orientational distribution function is basically Gaussian. Of course, for large theta, this can't possibly be true, because once you get to theta equals pi, it should be the same thing. So there should be things like sine instead of the theta. But for small theta, this is good enough. And then you can normalize the Gaussian. And this is what you put in. And then you can write. You can say, let's first start with a strange system. And this is not the way Theo Odak did it, by the way. You take a strange system where you say, I have a system of these rod-like molecules, and they have been aligned, for instance, by an external field. So you have this Gaussian orientational distribution function, and then you can write down the free energy of that system, which in this case, because it's an ideal gas, has only the rho log rho term. You write it down, and you get this. And as you see, the width of the Gaussian enters into the free energy, and the rest are trivial things. Now the way is, how do you deal with the interactions? And personally, I happen to like the Witham method very much, so I'll tell you what you do. You say, I compute the excess chemical potential of the system by looking at the following situation. I have these molecules, their orientation is distributed in a Gaussian way, so actually they're also infinitely long. And I'm going to insert one particle, an additional particle at random, and I look at the Boltzmann factor associated with the insertion. Now that, if you take minus kT times the log of that, you get the excess chemical potential. Now the way to do this, to make this easy, is to actually say, I'm going to assume that this particle is parallel to the z-axis. That's not completely true, because actually itself has an orientational distribution. But if you take this particle like that, then the whole calculation becomes extremely simple, and you can show directly that in that case this Boltzmann factor is nothing else than e to the power minus the number density of the gas times the average excluded volume, which for a Gaussian you cannot compute, because you just take the average, you integrate sine theta over this Gaussian distribution. And the excluded volume goes as the narrower the Gaussian, so the larger this A, the smaller the excluded volume, which is what you expect. So you have an analytic expression there, and then you combine everything. You get the Helmholtz free energy of the gas, including the interaction terms. The only thing is that we still have the width of the Gaussian as an adjustable parameter. So you say you minimize the free energy with respect to that parameter, and in the end, what you get is an explicit expression for the free energy, an explicit expression for the chemical potential, and from the free energy you get the pressure and everything. So this is just to show that with a very simple model, you can get analytical expressions for, well, certainly the isotropic phase, where they are analytical and exact, and for the pneumatic phase, analytical but not exact. And if you're on Saga, you get a smarter analytical approximation, but you can get them. And then, so in this particular case with the Gaussian, this is the chemical potential for the isotropic phase, this is the chemical potential and the pressure for the pneumatic phase, and you just basically make a plot of mu versus p for the two phases and check where they cross. And so, just for your amusement, I did that. And then this is what you see. Here you see the chemical potential, here you see the pressure. This is the intersection point for this Gaussian approximation that I just sketched, which actually, although it's not the way Odak derived it, gives exactly the same answer as Odak did. Onsaga's result gives you a slightly lower transitive value for the pressure. And if you take the exact result, and by exact I mean numerically minimizing the density functional, then you can get this. So these are, although they give you different answers, and the difference is up to almost 20% in the pressure, they all give you at least qualitatively the same answer. And it is an example where using a very simple model has helped you to understand something about this isotropic pneumatic transition. Sorry?
The Meyer-Saupe order parameters, that can be measured in an experiment.
Yeah.
How does it compare in the different models? Predict it?
Well, so if you look at the models give you explicit expressions. I didn't write them down, but they of course give you explicit expressions for the order parameter, and they are different. And I forget now. I mean, I think
0.7 something.
Yes, it is 0.7, but the exact result is I think it's the highest one of the transition. But I can't. Isn't it? Well, yeah, you know that. So you can get them. It's also true that certainly if you use this Gaussian model, you can get a very simple, effectively a simple dependence. I forget whether the order parameter goes as 1 over rho or 1 over rho squared, so 1 minus 1 over rho, something like that. So they have all very simple dependencies. In the Onsager case, it's a bit more complicated. But now I want to go beyond the nematic, and then it becomes really difficult, and that's where the simulations come in. Because this argument for the Onsager argument really only works because you can look at the isotropic nematic transition by saying I have a gas of particles, and they have excluded volume interactions. That basically means that if I look at the number density, let's say rho times L squared d, that is of order 1, but rho times L d squared, which is something like the volume fraction, is much less than 1, and eventually goes to 0. So you occupy a negligible fraction of the volume, and at the same time you have strong interactions between the particles because the excluded volume interactions are important. Now if you go to the more highly ordered phases like the smectic and the columnar, you're always in a regime where the volume fraction itself becomes large. And so you can't use the Onsager approach anymore. And so at the same time you would very much like to know for these things where in simulations you see that you go from nematic to smectic at some density, you would like to know what's the behavior in the limit of infinitely long rods. And is it still a smectic? I mean, there could be other possibilities. For instance, it could form a columnar phase where rather than the molecules organizing in layers, they could order in these these lines that themselves order in a two-dimensional crystalline lattice, or something else could happen. Let me just show you, for those of you who don't think about the columnar phase every day, just a few snapshots. Columnar phases usually are seen in the context of disk-like particles, although in a minute I'll discuss them in the context of rod-like particles. So this is a nematic phase of disk-like particles done in second millennium graphics, and then if you go to a high enough density, then this is what you get. These things stack in columns. They form a two-dimensional crystal lattice, but in the third dimension there's no long-range order, so it's liquid in the third dimension and crystalline in the other two. And you can do this. This is actually for a kind of ellipsoidal platelets, but if you do it for real disk-like particles, you get these very pretty pictures. And the color coding is due to whatever, usually the student or postdoc decides on the color coding, and I'm totally unable to do anything about it. Okay, so the thing is that we know from the simulations of rod-like particles that they have a low dimensional, for small aspect ratios between 3.5, 3.6, you don't get a nematic smectic transition at all. At some point, if they're sufficiently, if they're a bit like this piece of chalk, they start to form nematic and smectic phases, and then the simulations say up to an aspect ratio of about 100, we always see nematic smectic. But we don't know a priori whether that's still true if you go to very, very long rods. So what would happen if you take the aspect ratio going to infinity? Now the thing is, you see, that this is a bit of an issue with simulations, because if you have an if you have an infinite aspect ratio, still in the simulation box you say these particles have to fit in. So you want the simulation box to be at least large enough to accommodate the particles. The naive argument would say you need a box volume of order L cubed, and the number of particles is that the volume per particle is of order LD squared, because the volume fraction is not negligible, and therefore the total number of particles in such a simulation would go as over L over D squared, and that goes to infinity. So if you go to this huge aspect ratio, you run into problems because the number of particles that you have to simulate diverges. And so you'd say, that's bad news, you can't do it. Now in fact you can, and that's, I mean, that is something that still after more than 10 years I like to tell you because I think it's really interesting. And so what do? You say, well, if I am in this very dense nematic phase for a very long rod, they're very, very, very strongly aligned. And so this angle theta that they make with the director becomes very small, so small in fact that if you do an affine transformation where you rescale the z-axis by a factor d over L, you map this particle. Now of course the sphere immediately is squashed to be, it's flat, but the rod becomes a cylinder. Now it's a hard, a right cylinder, so it no longer has a hemispherical cap. And of course, this distance here is still preserved. So this would project down to here, but the distance over which this moves remains finite. It doesn't go all the way through the simulation box. So this is the thing that I will not go into detail to show. These fluctuations are sufficiently small that actually you can completely rescale your simulation box in one direction and then still do the kind of terrible things you want to do. And I mean, for serro cylinders, they are terrible. And actually, if you're good in your mythology, you know that it's actually totally ancient technology. You have here Hotel Procrustes, and of course, Procrustes, as you may know, had it bad. And if you had particles or people arrive with the wrong size, then Procrustes would do an affine transformation, so here, and make sure that the person did that. Basically, that's what I'm doing. I'm doing a Procrustean simulation. If you do that, then I'll just show you a few snapshots because they say more than what I can say. This is a nematic phase, but now for this box that used to be infinite in that direction, and now it's finite, so that all these particles have a length 1, but the angle, the fluctuations are still possible. So you see these things, they fluctuate, but they don't fluctuate wildly. So this one, pretty wild, but they don't go all the way through the box to the other side. So this is a doable simulation. You increase the density, and this is what you see. You see layers forming. So actually, there is still a transition from nematic to smectic, and for those who are into phase transition, you of course want to know, is that the first order phase transition, which actually for nematic to smectic is not. I mean, has always been a bone of contention. In this particular case, we have some evidence that it's first order, and the kind of evidence that we have is that in this case we look at the here you see the difference. This is the smectic order parameter in this direction. This is the free energy. For small systems, you don't see a hump in the middle. As you make the system larger, you see a hump appearing between the nematic and the smectic phase, and that typically is an indication that you're most likely at the first order phase transition. So this is the pedestrian first steps of Binder's finite size scaling analysis applied to this transition. I mean, I think that if we would do it now today, we probably would do it for much larger systems, much more systematically. But the evidence is that the transition of rods at high densities for a large aspect ratio, for infinite aspect ratio, is still a nematic to smectic, and secondly, it is still first order. The last thing I want to say about this transition is that, of course, if you look at experiments, people have done experiments on the transition nematic to smectic with virus particles. So Seth Freyden and his collaborators have worked with the FD virus, and they say, what's the effect of flexibility? You can even do the same transformation, this Procrustean simulation, if you take semi-flexible particles, unless you make the flexibility too large. But if you take a sufficiently inflexible semi-flexible particle, you can do exactly the same. You get these strange aligned worms, and you can look at their phase transition, and then we still find exactly the same, that these things still undergo a first order. Sorry, I can't say here about the order. We didn't do that in that analysis. We still find nematic to smectic transition. So, just to go on, is there a way to get a columnar phase with rods alone? And so it seems that for rods, if you have rods of a given length, it doesn't work. If you have rods with flexibility, it doesn't work. So we need something else. And the thing that we need to make a columnar phase is polydispersity. Polydispersity, for those of you who don't use these terms regularly, is the fact that you have that particles have different sizes. In this case, if you have rods, you can look at particles with different diameter or particles with different length. And we'll be looking at a situation where particles have different lengths. So here you have a smectic phase of particles with all the same length, and here you have a smectic phase of particles with all different lengths. And you can see that larger gaps result. And that kind of formation of gaps is something that you would not have if you have a columnar phase. So here you have a columnar phase of particles with all the same length, but we know that they don't form for particles, rod-like particles with the same length. However, if you have particles with all different lengths, then you see that they can still fill space quite efficiently, even though they're all different lengths. And again, human experience has prepared us for this, because here you see an example of a columnar phase where you can easily mix lorries and passenger cars. But if you actually want to make a smectic phase, and the closest thing to a smectic phase is a parking lot, then you'll find at any parking lot that cars and buses are always separated. So they form smectics. So that's the human. So actually, and in this case, our human intuition is absolutely correct, because if you do the simulation, then this is what you find. Here you have the polydispersity, and so this is effectively a measure for the root mean square variation of the length of the particles compared to the average. So here they all have the same length, and this is 5% variation, 10%, 15, 20. And in this density, you actually see the density, and yet low densities, well, not very low density, but sufficiently low here. You have a nematic phase, then you undergo a transition to a smectic phase, and at high density you get the transition to the crystal phase, is what I showed before. Nematic, smectic, crystal. But as you make the particles more polydispersed, so the length variation is larger, then at some point you see that the smectic regime shrinks, and at the same time, at very high density, the crystal is also destabilized by the polydispersity, and at some point you go directly from the nematic phase to the columnar phase. So that is interesting, because it means that polydispersity, I mean, in experimental colloid science, if you really want to upset your colleagues, you sit and have a drink around the table, and you say, how about polydispersity? And everybody says, you wave a cross at a vampire. I mean, polydispersity is deeply and universally hated. Here, polydispersity is a very nice thing, because you can induce a phase that wouldn't exist without polydispersity. So I've become a great fan of polydispersity. I have only a few more things to say, which means there's lots of time for discussion. The thing is that I use my Procrustean simulation to look at the transition nematic to smectic for infinitely long rods. We can also look at the situation I showed you, the columnar phase of disks, actually, these are not really this, but the columnar phase of this. And again, you can ask the same question: what happens if the aspect ratio of the disks goes to 0, so that they become infinitely flat, but still you go to such high densities that the volume fraction remains fine. So this is one of those pathological limits. And it turns out that you can do exactly the same kind of trick. So here I sketched it very roughly. So here's my disk. It has a thickness h, and now what I do is I basically take my system and I scale the z direction, but now I blow it up. So I make the z direction, I do an affine transformation in that direction with the factor d over h, so that this length always becomes 1. And then all particles, it's like you have in the columnar phase a stack of cards. You can move the cards like this and like that in a stack, and I'm not quite sure. So in the width always remains the same. The only thing is that the things can move up and down, but these fluctuations remain finite. And you can then do a simulation of such a model. And I apologize that I don't have any pretty pictures at all, so I made it up myself. This is the way it would look. So different particles have different orientations, and therefore these angles are the same, the width are always the same, and this is a perfectly normal system that you can study in a simulation. And what do you find? You find that the transition from the pneumatic phase to the columnar phase is still there, so that even in the limit of infinitely thin platelets at sufficiently high density, you still have the same pneumatic to columnar transition. Now, of course, you can again say what would polydispersity do, etc., and I'm sure that there has been a lot of work since that I haven't followed, where people have been looking at some of these things. But the main thing is that you can consider this limit, and then you can see what happens to the limit if you start varying other parameters. The last, and now really last example that I will show is a bit different, because I will be looking at the limit that has nothing to do with changing the properties of the model, but looking at the properties of a model in a regime that you wouldn't normally look at. And that is looking at the solid-solid transition. Now, I should say a few things about the solid-solid transition. Actually, what I precisely mean is not a transition between two solids with a different structure, but between two solids with the same structure, the same symmetry. There are examples in nature, in particular in metals such as cerium and cesium, where such transitions occur because as you compress the solid, the metal ions in the metal go into a different electronic state with an effective different core volume, and so you could say the crystal collapses, but it collapses into another crystal with the same structure at sufficiently high temperature, which I think you can reach for cerium, but you cannot reach for cesium. You actually have a critical point, and above that you go continuously. You can, because as with the gas-liquid transition, the two phases have the same symmetry, so there's nothing that tells you that there should be a transition, there just happens to be one. Now, you can get exactly the same transition if you take particles, and in this case we think of colloidal particles with a short range attraction. If that attraction has a short enough range, then, and again I'll make a sketch here. So you have particles with an interaction potential that looks like this. Repulsion up to a distance sigma, so this is the distance, this is the interaction potential. And then a short range attraction like this, minus epsilon, I mean the precise shape actually doesn't matter, and then 0. So these are particles that only feel each other if they are at the distance between sigma and sigma plus a small number delta. And this delta is typically less than 5% of the diameter of the particle. Now what happens if you form a crystal, hard sphere particles freeze at the density in the liquid of 49 volume percent and form a crystal that is about 54 volume percent. If you have particles like that in a crystal, they are not sufficiently close for these interactions to actually kick in, because these are short range interactions. So they don't even know that there's attraction. They know it a bit, but not very much. But if you compress this stuff, then at some point all these things are getting sufficiently close that a central particle will say, hey, I have interaction with this one and that one and that one and that one, and suddenly the interaction energy that used to be 0 goes down to minus 12 epsilon, actually minus 6 if you do it per particle because of double counting, but it goes down quite drastically. And we know what happens if you have free energies where you have one part as a function of density. So this is free energy density. One part that goes like this, which is the denser it is, the higher the free energy. And another part that actually tells me about the interaction that says nothing, 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 whoop. Then the whole thing does this. And then we can do a double tangent construction. And so this is why we have these transitions. Okay, long introduction to show just one slide. And then the one slide I wanted to show is simulations we did a long time ago, and whenever I say we, I should stress it's the royal we, which means everybody else but me. In this case it was Peter Bolhuis who did, this is invisible. Except the crucial point is there. They're black dots, and I'll try to talk you through the black dots. So what you see here is the density, and 1.41, which happens to be the square root of 2, is the density, the Kepler packing density for spheres. So in units rho sigma cube, where sigma is the diameter. This is temperature. So at high temperatures, these attractions are important. You cool the system down. Actually, what you see, you don't see here, but I'll tell you that you should be able to see here a fluid. Then you see this line, which is the density of the coexisting fluid. Another almost invisible line. Here you get into the crystalline solid. And at high temperatures, that's it. At lower temperatures, there's actually transitions in the salt. And these black dots are the critical point. This is where this solid-solid transition ends. And above that, you go continuously from a low-density solid here to a high-density solid there. Now you see we did this for different ranges of the attraction potential. This is like 5%, I don't know, 3, 4, etc. And here you see it point at close packing. And that's the unphysical limit I want to talk about, but only very briefly. Because apparently we have been stupid enough to do a calculation for a phase transition at close packing. Now it's not really at close packing, but it basically is as close to close packing as you like to be. And so this is for instance interesting because you have the same thing with a hexatic phase. So near this, in 2 dimensions, near the solid-solid transition, there's a small pocket of hexatic phase. And so again, we can look at the properties at close packing to see what this phase does. Now, how can we do this? Here I've drawn the same system of hard particles with short range attraction, but rather than drawing all the particles the same size, I take the central particle and represent it as a point, and all the other particles, rather than giving a radius sigma over 2, I give them a radius sigma. But for the interaction, it just does the same thing. It basically means for the central particle, all this volume is excluded, and you have only this small hexagon in which it can move. Now, it's not really a hexagon if you're at low density, but the closer you are to close packing, the more it becomes a real hexagon. The only thing is that if these particles move in this direction, the hexagon becomes smaller in this direction. If this particle moves in this direction, or I should have lined it better, the hexagon becomes shorter in that direction. However, the orientations of the sides of the hexagons never change, because if you're in that limit, because the motions are so small, any small motion of a particle here is not going to change this angle. So you have hexagons, but they're strange deformed hexagons with, however, always parallel faces. So these faces are all parallel. And what you have done now is basically to map the whole model of a hard disk or hard sphere solid at close packing onto a lattice model. And so the only thing you have to do is to look at the displacements of the particles from the lattice sides. If they get, if the displacements are large enough, the relative displacements are large enough, they can attract. So you can look at this transition. Actually, this is if you have particles, for instance, move away from each other, they will not feel the attraction. If they move towards each other, at some point they will feel the attraction. And for this lattice model, you can easily then study the phase transition and find exactly the one point that I was showing. So with this almost invisible point at close packing was computed not by doing a normal simulation on particles moving in free space, but for this kind of strange model of vectors on a lattice. I still personally think that the critical properties of that system would be extremely interesting to study, because to me it's totally not obvious what it would be. And the reason why it's not obvious what it would be is because the solid-solid transitions, they look like normal liquid vapor critical transitions, so you would expect that you would have a the standard exponent, the standard 3D Ising exponent, or in this case 2D Ising exponent, except that you're in a crystal lattice, so you also have the elastic deformation of crystal lattice, and that may change the situation. The only thing is I don't know the answer. Let me conclude, and the conclusion is really, I'll let Onsager say it. He can't speak back, so I can easily let Onsager say it. Onsager simply says, consider limits in cases they're simpler and they provide insight. And with that, I'd like to thank you for your attention.
Many thanks, Dan. Questions now?
Yeah, you showed some simulation result basically suggesting that flexibility shouldn't allow for stability of columnar phases. But then I was wondering, how would you explain the stability of columnar phases in antivirus suspensions?
The answer is, I was aware of the experiments, and there have already been experiments for quite a while. The only thing I can say is that these findings suggest that it's something beyond the simple hardcore model. But I also should say that at the time that we were doing these simulations, they were considered to be very expensive. They're probably now dirt cheap, so maybe a more systematic study would be. For instance, I showed you only one value of the persistence length. Other values may give you other answers. So it's, as far as I'm concerned, an open question.
Why our pencils do not behave as liquid crystals? For instance, it has L over D 10.
Yeah?
Why it does not behave as a liquid crystal?
Pen? Does.
Yes. Under what conditions?
Okay, so if you have a pen with an aspect ratio 10, then and we tweak Boltzmann constants so that your pen is actually performing Brownian motion and everything, and the switch of gravity, then your pen initially will form a pneumatic phase, and as you compress it more, it will form a smectic phase, and as you compress it even more, it will form a crystalline phase, except that you have this small wiggle at the side of the pen, and that may screw things up a bit. So I don't quite know what it will, but roughly, certainly pneumatic would form, smectic probably would form, and beyond that, it probably is going to be a bit different.
So can you comment on the role of having attraction in? Is it just, can you use it just as a perturbation, or is it going to a totally different pictures? For the viruses, you would expect a marker to switch in.
Well, actually, in many cases, I think it is just a perturbation, but if you look, for instance, at the solid-solid transition, without the attraction, it's simply not there. So there, it's everything. So
for surface tension, I guess.
Well, absolutely for surface. I mean, if you have no attraction, or at least I would say no effective attraction, it need not be energetic. It may be entropic, but if you don't have an effective attraction, there will be no surface tension. Absolutely. So there are many things where you absolutely need attraction to get the physics right.
Is there a critical polydispersity to go from a smectic to a columnar?
In the picture that I showed, it's about 15%. So as far as I can easily go back, but I mean, that was
15 is enough to describe as smectic, isn't it?
That's right. So the 15 did exactly that. Where was it? I think it's this one. Oh, now we get this again. Well, maybe it'll come back, maybe it won't. Oh, there it is. See, so between 15.
All right, we've got it on.
Yeah, yes. Mike.
Right at the end, you were referring to that interesting nearly close pack phase
Yeah.
of a hexatic phase. Does that mean that you can detect free dislocations and defects like that?
The answer is no, of course not. I mean, maybe we shouldn't say of course not. But whenever people do studies of the hexatic phase and they say, see, look, I see free dislocations, then they're not looking at the transition to the hexatic phase. The one way you can recognize the transition from the solid to the hexatic phase is by the fact that you don't see anything. The only way you can tell that you're actually at that, because what the hexatic phase actually means is the transition to hexatic happens at the moment when you can get an infinitely dilute gas of dislocations are unbound, and it's only the dislocations the very largest dislocation dipoles that can unbound. Everything else is still bound. So it looks like a normal solid, and the only way that at least I can tell whether I'm likely to be in a hexatic phase is by computing the elastic constants and check whether Young's modulus drops below the magical value of 16 pi. Now the thing is, in the simulation you'll find an answer that is wrong. However, you know that if you go to a larger system, it will be renormalized downwards. So if in the simulation you find something that is 16 pi, you can be pretty sure you're in a hexatic phase. That's my way. Yes.
Next question.
Could you suggest a limiting model for the biaxial pneumatic phase?
I would think that you can do essentially this. Well, let me not speak too quickly. Cameras switch off now.